Today's topic is what we have to find electric potential at a point on the equatorial line of an electric dipole. In this case, we have considered an electric dipole AB of length 2L, consisting of negative charge and positive charge, minus Q and plus Q. They are separated by a distance L, and we consider this equatorial line and P be a point at a distance R. So the distance of the point P from the midpoint O is R, x is equal to R, and distance of the point D from the midpoint O of the dipole is what at this point, what is the value of distance? X is equal to infinity, and R is the distance of the point P from O. And here, what is EEQ? Field intensity at P on equatorial line of this electric dipole, and which acts in the opposite direction of dipole moment. Dipole moment P acts from minus Q to plus Q charge, and field intensity at this point is EEQ. So here the electric potential at which point at P on the equatorial line of an electric dipole AB is denoted by VEQ, which is equal to work done in bringing plus one charge, unit positive charge, from infinity means which point? The point D. From infinity means from point D to the point P along the equatorial line. And we know that work done is integration force into displacement. In this case, force is vector EQ, field intensity on equatorial line, into displacement is dx, vector dx. And limits will be what? Infinity to R. Where what is EEQ? Expression of EEQ, we know that field intensity is 1 by 4 pi epsilon 0 dipole moment divided by R square plus L square to the power 3 by 2. This is field intensity at P or D, field intensity on equatorial line. Field intensity at D, where x is what? R is the distance. Here we can write x, not it should be x square plus L square. Distance is x here. Now infinity to R, EEQ dx cos 90 degree. In this case, what force on this unit positive charge acts in the opposite direction of dipole moment vector P. Dipole moment vector P acts along AB from minus Q to plus Q charge, but EQ acts in the opposite direction, and displacement of the unit positive charge occurs along the equatorial line. So obviously force acts perpendicular to the displacement. That's why we have written cos 90 degree. That is 0. So we get the electric potential, expression of electric potential at a point on equatorial line, that will be 0. Hence it is 0. This is potential potential at a point, in this case which point, the point P on the equatorial line of an electric dipole, So mainly electric potential will be zero at any point on the equatorial line, because force on unit positive charge, that means field intensity, acts at right angles to the displacement of unit positive charge. That's why electric potential is zero. We can prove this result alternatively. So we have considered the same diagram, and in this case this distance PV is root over r square plus L square, and it is also root over r square plus L square. At P we have to find electric potential VEQ. So now same way, the electric potential at P on the equatorial line of the dipole under bracket AB is VEQ is equal to potential at P due to plus Q charge plus potential at P due to minus Q charge of the dipole AB. So now what will be the equation? Here expression of potential is charge divided by distance 1 by 4 pi epsilon naught. Positive charge is Q2 divided by distance is this distance PV. BP 1 by 4 pi epsilon 0. It should be Q2 and this is Q1. Negative charge means Q1 divided by AP. This is Q1. Now 1 by 4 pi epsilon 0 is taken common, and in place of Q2 what we can write plus Q, and BP means root over R square plus L square, and Q1 is minus Q root over R square plus L square. Here we have considered and this charge is minus Q, obviously. We have considered the sign of the charge in the expression of potential. Q1 is minus Q and Q2 is plus Q. If it is, if we have to find field intensity, in that case we cannot consider the sign of charge. But for potential or work done of energy, we have to consider the sign of charge. That's why Q1 equal to minus Q, Q2 equal to plus Q. And this is 1 by 4 pi epsilon 0. And it will be same, so 0, VEQ equal to 0. That's why potential at a point on the equatorial line of an electric dipole is 0.